Welcome everyone. In this lecture we will continue our discussion of the application of Lyapunov theorem to study the stability of equilibrium points. We have stated before that Lyapunov theorem provides just a sufficient condition to investigate the stability of an equilibrium point. Also, we have stated that there is no general technique to suggest a Lyapunov function. However, in this lecture we will see some typical techniques that could be used in many applications. Also, we are going to provide the invariance principle, which is like a complement of the Lyapunov theorem in our context. So it will help us to provide additional condition to ensure asymptotic stability of the equilibrium point in case that Lyapunov analysis doesn't lead to that conclusion. And we have seen an example for this as applied to the pendulum problem. So we are assuming that we have a system, an autonomous system, x dot equals f of x, where x belongs to a real space of dimension n. Of course, we typically assume f to be locally Lipschitz over a domain D. And we assume that the equilibrium point is at the origin. So that is at 0. Now we investigate the stability of that system by proposing v of x, which is a positive definite function, and if v dot is negative semi-definite over the domain of interest, then we conclude that the equilibrium point at the origin is stable. However, if v dot is negative definite, then we conclude that the equilibrium point is asymptotically stable. If we select v of x to be radially unbounded, that it goes to infinity as the norm of x goes to infinity, and we have v dot less than 0, then in that case we can conclude global asymptotic stability of the equilibrium point at the origin. And again, we have mentioned that this could be the case if the system has only one equilibrium point. As I mentioned before, there is no general technique that can be applied for any system to construct a Lyapunov function. However, there are some guidelines. For example, in electrical and mechanical systems, we can always choose the energy function as the candidate Lyapunov function. Frequently, especially in adaptive control applications, we will get a quadratic form like this. It is 1/2 x transpose px as a candidate Lyapunov function, where p is a symmetric real matrix, and it is said to be positive definite if it satisfies any of the three conditions that I'm going to state right now. The first condition, if we have x transpose px positive for all values of x such that x is not equal to 0, or if the eigenvalues of p are real and all positive. And the third possibility, if we calculate the minor determinants of the matrix and we find them all to be positive, then again the quadratic form x transpose px is positive. By the minor determinant, I mean to take the first element 1 by 1, second element 2 by 2, and then the whole matrix if it is 3 by 3. So in that case we will find every determinant to be positive. If this is satisfied, then we say that p is positive definite. One of the techniques that could be systematically used to derive a Lyapunov function is the variable gradient method, and this technique could be well applied to small scale problems. So as we know, v dot, which is the derivative of the candidate Lyapunov function v, is the partial derivative of v with respect to x times x dot, and partial v partial x is actually the gradient of the scalar function v. So I'm going to represent it by a vector, a row vector g transpose x times f of x, since we know that x dot is equal to f of x. So the component of the gradient would be the partial derivative with respect to x1 up to the partial derivative to xn, and that would be multiplied by the vector field starting at f1 up to fn of x. Of course, I'm assuming here that x belongs to a domain of dimension, a real domain of dimension n. So we call this g1 of x up to gn of x, and that multiplies f1 of x up to fn of x. So we choose the gradient g of x to be the gradient of a positive definite function v of x, and we require v dot to be negative definite. So required that v of x is positive definite and v dot of x is negative definite. Also, we notice since the function v is scalar, then we can calculate the Jacobian of the vector, the gradient vector g. So we will notice that the resulting matrix, the Jacobian matrix, will be symmetric, and that means that the partial derivative of gi with respect to the state xj would be equal to the partial derivative of gj with respect to the state variable xi, and here I and j will run from 1 up to n. So this property follows from the fact that v of x is a scalar function. So now we would like to choose G transpose x times f of x to be negative definite, and consequently we compute v of x as the integration from 0 to x of G transpose of y dy. Of course, y here is a dummy vector, and we can do that along any line that joins 0 to x. So normally this is done along the main axes of the coordinate system. So that will lead to an integration from 0 to x1 of g1 of y1, and put all the other state variables equal to 0 and with respect to uy1, plus the integration along the x2 axis from 0 to x2 of g2 of x1 y2, then zeros dy2, and that will continue till the integration across the variable xn axis from 0 to xn of gn x1 x2 so on up to xn minus 1 and yn dyn, and of course that has to be positive definite. So, example is a generalization of the pendulum equations. We can see here that we put in general a nonlinear function h of x1 instead of the sine function that appeared in the pendulum equation, but otherwise the modeling equations look similar. We assume here that the constant a is positive, and that the nonlinear function is locally Lipschitz, and we assume that y times h of y, which is the product of the nonlinear function by its argument, will give us a positive answer. And the meaning of that is that if we assume here the axis y and hy, so that means that the function will appear in the first and third quadrant, and also because of the continuity of the function, then it has to go through the origin. So the function will look like this, and later on we will use the fact that the integration from 0 to the value of y would give us area under the curve which is positive, so that will be used in our coming analysis. So anyway, we are assuming that y times h of y, the nonlinearity follows this relation, and we assume that the function is defined over some open interval from minus a to c, where a and c are positive constants. So now, in order to start applying the gradient approach, we are going to assume that the gradient of v is composed of, in our case, two nonlinear functions, g1 of x and g2 of x. Now, since g is the gradient of a scalar function, as I mentioned before, that means that the Jacobian will be a symmetric matrix, and that will mean that the partial derivative of g1 with respect to x2 should be equal to the partial derivative of g2 with respect to x1. So this follows from the symmetry of the Jacobian matrix. We know that v dot is g transpose multiplied by the vector field f, so that gives us g1 of x times f1, which in our case is equal to x2. This is f1 of x plus g2 of x times f2, and that's minus h x of x1 minus a x2. So that has to be negative definite. We also know that v of x is the integration from 0 to x1 of g1 of y1 and 0 dy1 plus the integration from 0 to x2 of g2 of x1 and y2 dy2, and that has to be positive definite. Here we have to make an assumption regarding to the form of the gradient. So let us assume that g of x, which is a vector composed of two elements, will have phi1 of x1, so a nonlinear function phi, in general a nonlinear function phi1, which is a function of x1 only, and another nonlinear function psi1 of x2, and similarly the second element will be phi2 of x1 plus psi2 of x2. So this is our assumption here. Now we can then take into consideration the symmetry property of the Jacobian. So the partial derivative of g1 with respect to x2 should be equal to the partial derivative of g2 with respect to x1. So we'll do that. So now if we take the partial derivatives, that would lead to the partial derivative of psi 1 as a function of x2 with respect to x2 should be equal to the partial derivative of phi 2 of x1 with respect to x1. Now again we can select arbitrarily psi 2 and phi 2 so that it would satisfy this equality. So I'm going here to assume or choose psi x2 as some constant gamma times x2 and phi 2 of x1 as the same constant gamma times x1. Obviously when we differentiate, the result would be gamma in both cases, so we would achieve or satisfy the symmetry of the Jacobian matrix as required. And if we do that, we can now calculate an expression for v dot. So v dot will be phi 1 of x1 plus gamma x2. This is the psi 1 that we have just assumed, and that's multiplied by x2 plus gamma x1 plus psi 2 x2, and that multiplied by minus h of x1 minus a x2. Now we can do the multiplication, and I will arrange terms that have x1 only and x2 only together, and terms that have cross product of the two variables together. So that will give us minus gamma x1 times h of x1 minus a x2 psi 2 of x2 plus gamma x2 squared. So these are terms that include only one variable each. Then we'll have other terms that will have cross products. So that will be plus x2 phi 1 of x1 minus psi 2 of x2 times h of x1 minus a gamma x1 x2. Now what I'm going to do, I'm going to select phi 1 and psi 2 such that I can get rid of the cross terms. So let me select psi 2 to be delta times x2 and phi 1 to be delta h of x1 plus a gamma x1, and see what will happen. We'll substitute again in v dot. So we get v dot equals minus gamma x1 h of x1 minus a x2 psi 2 of x2 plus gamma x2 squared, and then the substitution with the suggested values for psi 2 and phi 1 will lead to delta h of x1 times x2 plus a gamma x1 x2 minus delta x2h of x1 minus a gamma x1 x2. So we can see here that these two terms will cancel, and also we have these two terms also to be cancelled. So we will be left with an expression for v dot as minus gamma x1 h of x1 plus gamma minus a delta x2 squared. And of course we require this function to be negative definite, so we already assume that x1 times h of x1 is a positive quantity. So this, if we select gamma to be positive, then this term, the first term here, will be negative. And also by proper choice of delta and gamma, we could make sure that the second term is also negative. So we have to select actually gamma to be less than a times delta. So that's why we left the constant gamma and the delta free, so that we can select them later on and achieve our requirements. Now we have to find v of x, and that is done by integration, as we mentioned. So we integrate from 0 to x1 g1 of y1 and 0 with respect to dy1 plus the integration from 0 to x2 g2 of x1 and y2 with respect to y2. So we substitute here by the values of g1 and g2 as we have calculated them. So the first term will be integration from 0 to x1 of delta h of y1 plus a gamma y1, and here we integrate with respect to y1, and then plus from 0 to x2 gamma x1 plus delta y2, and this is y2. Of course, the expression I wrote here is g1, and the expression I wrote here is g2 of x, after substituting by the appropriate expressions in the phi and psi functions that I have assumed at the beginning. So if we do this, we get 1/2 a gamma x1 squared, this is from the second term here, plus delta, the integration from 0 to x1 h of y1 dy1. And remember, I mentioned at the beginning that because of the assumption on the nonlinearity h, this integration will give us a positive positive result. So multiplied by a delta which is positive, that overall will be positive as required. And then the integration for the second term will have gamma x1 x2 plus 1/2 delta x2 squared, and that comes from the second term here. Now we can rewrite this as 1/2 x1 and x2 times A gamma, here is gamma and delta, is multiplied x1 x2 plus delta integration from 0 to x1 of h of y1 d y1. Now, in order for this function to be positive definite, we require this matrix to be positive definite. And as I mentioned before, this would be a positive definite if all minor determinants are positive. So we require, of course, gamma to be positive. A is already positive as assumed at the beginning. And then we require A times gamma delta minus gamma squared to be positive, and that will require A times delta to be greater than gamma. So this way we have achieved both requirements. We have achieved that v dot is negative definite and v of x is a scalar function which is positive definite, and then we can conclude that the system is asymptotically stable at the equilibrium point. So now let's move on to the invariance principle, which, as I mentioned before, is a tool that we can use with the Lyapunov theorem to establish the asymptotic stability of the equilibrium point at the origin. Now let us recall the pendulum equations, the second order equations that we have seen before, and we have selected the function v, which is positive definite, and it consists of the potential energy and the kinetic energy for the system. We calculated the time derivative of v, and we have shown that it is negative semi-definite. It's minus bx2 squared. So it is equal to 0 if the state variable x2 equal to 0. But x2 actually is nothing but the velocity of the pendulum. In order for the velocity of the pendulum to maintain zero velocity, then we have actually to assure that the acceleration is equal to 0. The acceleration is x2 dot, and in that case, if we put x2 dot equal to 0 and x2 equal to 0 in the second equation here, then we'll get x1 equal to 0 as well, and that's of course in the range of x1 between minus pi and pi. So we conclude that to maintain the system at the equilibrium point, we should have both x2 and x1 equal to 0, and consequently the equilibrium point to be asymptotically stable. So that's exactly what the invariance principle will try to establish. It will try to see that in a domain around the origin, if we can find a Lyapunov function whose derivative along the trajectory of the system is negative semi-definite, if we can establish that no trajectory can stay at v dot equal to 0 except at the origin, then the origin is asymptotically stable. Now the argument which I just have mentioned is an application of the invariance principle, as we are going to see. However, before we do that, we have to have some definitions regarding the different sets that we are dealing with. First of all, we are going to define what's called invariant set, and this is a set which we may call it set M. It is invariant with respect to the solution of the system, the autonomous system equation x dot equals f of x, if the states will remain in that set for all time that belong to the real axis. So that means all positive and negative time, the states as defined on that autonomous system will remain in the set M. Now, Examples of this would be the equilibrium points and the limit cycles, because if we have a system at its equilibrium point, then it will remain there forever. Also, the limit cycles, if the system has its trajectory on the limit cycle, then it will remain for all the time in that limit cycle. We also define what's called a positively invariant set, and this is again a set M which is positively invariant if the system trajectory enters that region, it will never leave it. So here we require that the system will remain in the set M for all positive times. So the basic difference here is that this is defined for the positive time, while in case of an invariant set, it is defined for all time positive or negative. And an example of the positively invariant set is the set where defined by v of x less than some constant c, and v dot less than or equal to 0, and a negative semi-definite value for v. So this set will define a positively invariant set, because if the system trajectory enters that set, it will remain there afterwards. Now I'm going to introduce Lassalle's invariance principle, and I'm going to follow the presentation by Hassan Khalil in his book Nonlinear Control, chapter 3. So we start by assuming a domain. I'm going to call that domain D, and it is a subdomain of the real space of dimension n. So we select within that domain a compact set. We call that omega. So omega is a compact set, which means that it is bounded and closed, and it is a positive invariant set with respect to the autonomous system x dot equals f of x. That of course means that if we start with an initial condition within the domain defined by omega, then the trajectory of the solution will remain inside that domain. Now we also define over omega a function v of x. So this is defined over omega such that v dot of x is less than or equal to 0. This is the only condition imposed on v of x. It doesn't have to be positive, definite, or anything. It is a function with its time derivative negative semi-definite, as I have indicated here. Now within omega, we define a region. I'm going to call that region E. So within that region, we will have v dot equal to 0. And inside that region, I'm going to define another region. I'm going to call that region M, which is the largest invariant set within the domain. So M is the largest invariant set. So according to Lassalle's principle, if the initial condition of the system started within omega, then as time goes to infinity, it has to converge to the region M, which is the largest invariant set. So this is basically what Lassalle has stated in his theory. In order to show that the trajectory of the system will converge to 0 as time goes to infinity, we need to prove that the largest invariant set in E is the origin. So this is usually done by showing that no solution can stay identically in the region E except at the origin. And this is actually done through the following theorem, which is a specialization of Lassalle's invariance principle, but it was actually shown even before Lassalle's invariance principle by Barbachin and Krasovsky, but it follows from Lassalle's invariance principle as well. So according to that theorem, we are going to assume that we have a locally Lipschitz function f of x, which is defined over a domain D subset of Rn. So let us assume that this is D, and the origin is an element in that domain, and it is the equilibrium point, as f of 0 will be equal to 0 at that point. And we define over the region D a positive definite function v of x. So this would be the candidate Lyapunov function, and we can show that within the domain D v dot is negative semi-definite, so v is actually a Lyapunov function. And we try to find a subset within the domain D. We call that subset S, where v dot equal to 0. So here v dot will be equal to 0 within the red domain. So if we can establish that no solution can stay in the domain S except at the origin, then we conclude from that the origin is asymptotically a stable equilibrium point for the dynamical system x dot equals f of x. Now, if we assume that we have again a subdomain gamma, which is subset of D, and that subset gamma is compact, so it is bounded and closed, and it is positively invariant with respect to the dynamical system x dot equal f of x, then actually that domain gamma is a subset of the region of attraction for the system under study. Further, if we can show that the domain D that we have selected at the beginning could include the whole real space of dimension n, and if v of x is radially unbounded, so instead of concluding asymptotically stable equilibrium point, we could actually conclude global asymptotically stable equilibrium point for the given system. So let us consider an example to illustrate the application of the previous theorem. We are considering here a second order nonlinear system. This could be a generalization of the pendulum equation. It could also represent a mechanical system that consists of a mass, damper, and spring if the damper and the spring are nonlinear elements. It could also represent the equation for the RLC circuit if the capacitor and the inductor are nonlinear elements. So we have here typical assumption like H1 and H2 are locally Lipschitz, and we assume that the value of H1 and H2 are 0 at 0, and the product of x times H1 of x is positive for non-zero values of x, and that is in the range of x less than a, and x dot H2 if x dot positive for x dot not equal to 0, again for the absolute value of x dot less than a. So we can rewrite this equation in the form of first order differential equations. So I'm going to take x equal to x1, and x dot, that would be x1 dot, take it to be x2, and x double dot, that will be x2 dot, and I will substitute from the original system equation, so that will be minus h1 of x, but x is x1, minus h2 x dot, which is x2. So we have here, this is the first equation, and this is the second equation. Now the equilibrium point can be shown to be at the origin, And our objective here is to verify that the equilibrium point is asymptotically stable, and of course we are going to use the invariance principle. In this kind of systems, we can always take a candidate Lyapunov function to be an energy-like function. So I'm going to take the function V as the potential energy, which in this case would be the integration from 0 to x1 of h1 of y dy, plus the kinetic energy, which is 1/2 x2 squared. So if we calculate V dot, that will give us h1 of x1 times x1 dot plus x2 times x2 dot. Now we can substitute for x1 dot and x2 dot from the system equations. So x1 dot is x2, so that will be x2 times h1 of x1 plus x2 times minus h1 of x1 minus h2 of x2. Obviously this term will cancel with this term, so we are left with minus x2 h2 x2. But since x2 times h2 of x2 is positive, then v dot is negative semi-definite. It's negative semi-definite because x1 does not appear in the expression of v dot. So in order to verify the equilibrium point at the origin is asymptotically stable, we try to look at the set where v dot equal to 0. And of course, v dot will be equal to 0. That will correspond to x2 equal to 0. So let us define the set D, where the magnitude of x1 less than a and magnitude of x2 less than a. And we know that V is positive definite in that set. And we defined a set S where this is a set of x1 and x2 such that V dot equals 0. And of course that would correspond to x1, x2 when x2 equal to 0. So now we try to find the solution that belongs to S and will remain in there. So if we take x2 equal to 0, that would require x2 dot equal to 0 in order for the solution to remain at x2 equal to 0. So if we do that from the system equation, if we put x2 dot equal to 0 and we know that x2 equal to 0, that will lead actually to h1 of x1 equal to 0, and that will happen only if x1 is equal to 0. So that implies h1 of x1 equal to 0, and that means x1 equal to 0. So that means that the only solutions that can stay identically in the set S is the trivial solution at the origin, and hence we conclude that the origin is asymptotically stable as required. So that shows an example where we can use the invariance principle to prove that the equilibrium point is asymptotically stable.